Okay, so my talk today will be about high-string topology operations, and it is based on the paper of the same name by Gorinin. And so,
actually, I don't see a translation of that. Well, now it appears.
Okay. There might have been a bit of a lag. Okay. So let me start. We will study some manifold M, an oriented manifold M of dimension D, and what we want to do is to construct some operations on the homology of its loop space that come from some what is called an open-closed cobordism between one-dimensional manifold. So let me define what these cobordisms are. So assume we have a two-dimensional oriented surface with boundary, and we will divide this boundary into three components. So we'll have the incoming component, we'll have the outgoing component, and we'll have the free component. And so essentially, this will be just a cobordism between two one-dimensional manifolds with boundaries. So you can look, let me paint some picture. So for example, here we have as the incoming boundary the union of a circle and two intervals, and I don't know, here we have two circles and one interval, and then for example we have something like that, and probably there are some handles. So yeah, so in this picture, this is the incoming boundary, this is the outgoing boundary, and the free boundary, which is this, is just a cobordism between the boundary points of this thing and this thing.
I don't understand from the picture what happens on this middle curve.
This one.
Yeah.
So, so this. Wait a minute. I think the picture is that you kind of, it goes like this. So you imagine that there was something and you just got it. So this curve, it can be glued by kind of two-dimensional thing that looks like this.
Something behind this.
Yeah. So like this is the front part of this, yeah, and then here's the back, yeah. Okay. So it might look like this, and then what we want to consider is the mapping class group, which we will denote by mod S or mod open closed of S, and by definition it is just the connected components of the group of orientation preserving diffeomorphisms of this surface, which also preserve the incoming and the outgoing boundary point wise. So I have such a mapping class group, and notice also that there is, so for example, if we have two open-closed cobordism S1 and S2, and the outgoing boundary of this cobordism coincides with the incoming boundary of this one, then we can produce their I believe it is called connected sum. And if we have such connected sum, then we of course have such an such a homomorphism. So yeah, so this is something trivial. Okay, and so
It acts identically on the boundary.
yes, it preserves each point. Yes. So kind of our main theorem will be the following: that the pair, the homology of the free loop space and the homology of M itself can be endowed with has a structure of a degree D open closed homological conformal field theory with positive boundary. So now I will explain what this means. So first of all, for each such a cobordism, we can associate a map mu S, which will act from the homology of our mapping class group, of the classified space of the mapping class group of S, with some twisted coefficients. D is the degree of the manifold. Then we tensor it with the homology of the free loop space times some number p, and it is tensored to the homology of times q, and then it goes to the homology of the free loop space with the tensor power of some number m, tensored by homology of m with some number n. And so here the numbers p and q are the numbers of circles and intervals in the incoming boundary, and the numbers m and n are the numbers of circles and intervals in the outgoing boundary. So this is just the homology of it's isomorphic to the homology of maps from the incoming boundary to M, and just the same, this is isomorphic to the homology of the space of maps from the outgoing boundary to M. Okay, so these are our operations. And so let me define what this twisting means. So so consider a virtual vector space Vs, which will be just isomorphic to the homology of S modulo the incoming boundary, and this just means that we take a virtual vector space which is the zeroth homology, homology minus the first homology plus the second, and so on. So I have this virtual vector space, and of course we have an action of mod S on this space, and so because we have that P1 of P mod S is just isomorphic to mod S, then we kind of can take this virtual vector space, and because we have a well-defined action of pi1, we can define a virtual vector bundle over the classified space. Okay, so we have such a bundle, and then we can take its determinant bundle. Yes, and then we want to define its determinant bundle, that here of S. And how we do it, we just take the determinant of this space. So if we have a virtual vector space, for example, V minus W, then by definition the determinant of the space is just V to the exterior power of n times V dual W, sorry, yeah, W dual to the exterior power of m, where the n is the dimension of V and m is the dimension of W. So this is just a one-dimensional space, and hence the determinant bundle is a line bundle. And so once again, it's just constructed by taking the virtual vector space of this thing and then constructing a bundle over the classified space from the action of pi1.
Yeah, but by the way, this formula is not correct.
It's not correct. In what way?
What is check here?
It is dual. Maybe, I don't know.
No,
No?
it's not correct.
Correct.
No.
Okay.
K theory minus bundle is not dual bundle.
Then why is it not correct?
It's correct for one-dimensional vector spaces.
But the dual commutes with the top wedge. So
I mean, you
maybe it's
want to
better
say
like
that
this.
the top wedge
First take the top wedge
and then take the dual.
Is that better?
Yes.
Yes. Okay.
Yeah.
Okay. So.
And this MS is of degree D or what?
It's degree D. No, it must preserve the degree. Yeah. Mu is a degree preserving map. Yeah. Okay. So once again, as I've said, the two upper class cobordisms can be glued together, and our operations should Как будет уважать по-английски? Я прошу прощения. Уважать. Yeah, should respect this gluing. I'm very sorry. Okay, so now let's say in which way they should respect it. So first of all, if we, I think I can erase this. So. So if we have two compatible open class cobordisms, then we have an identification of these bundles. One tensor Z, tensor tensor Z, which identifies with S2 as Z. So, oh no. I was thinking really bad. So here, of course, it is like this. And so this identification comes from the long exact sequence of the triple S1 the connected sum, then we take just think S1 and the incoming boundary of S1. Yes. So just if we write out the longest exact sequence of this triple, then we have a connection between the homology groups, which are virtual vector spaces, and from this connection comes this identification. And so because we have this identification, we can now show how our operations compose. So where should I do this? I think here. So we have the following commutative diagram. So first we take the homology of B mod S2 with the twist in. So just maybe I shouldn't try to twist in because I won't have enough space. So we have the homology of the classifying space for S2, then we tensor with the homology of the classifying space for S1, then we tensor by homology of the loop space to the power P by homology of M to the power Q. Okay, so then here we have the homology of the classifying space for the sum, tensor with Q, and then this goes to homology of some other power, then some other power. Yeah. Okay, so now what is going on here? This first map sends this tensor product to this homology through the identification that we've of the twistings that I've talked about just right now. Then this map is just the operation for the surface S1 plus S2, and then this map is given by composing the operations for S1 and S2. So we just first we apply kind of this part of the operation, then we get the compatible powers with this operation, and then we apply this operation. Okay, so kind of, I believe that if you think of a homological conformal field theory as a functor, then just this part of the theorem states how it acts on objects, and then this part of the theorem is just functoriality. Okay.
I would rather have said you've specified in the very beginning what happens on objects. The circle
Yes.
goes to homology of the loop space, the interval goes to homology of M.
Yeah.
Is that correct?
Yes.
Then this is telling you where the morphisms in your category goes, and this is telling you they compose well.
Okay. Yeah. Yeah.
Because the morphisms in your category would be homology of this classifying space.
Yeah. Okay.
But, so the assertion is that the two ways to get from the top to the bottom are the same.
Yes. 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 So this diagram commutes. Okay, so now let's look at some examples of this. So,
Sorry, before we go on.
yeah.
You defined mod to be pi zero of orientation preserving
Yes.
diffeomorphisms. In nice cases, the group of orientation preserving diffeomorphisms for a surface is homotopy discrete. It has no higher homotopy.
Yes.
And so these are kind of the same in a homotopical sense. Does she make any comment about this in general? Like if you put in these funny surfaces with weird boundaries, you suddenly pick up pi 1 in the diffeomorphism group? Or?
I don't. I don't believe so, but
She just defines it this way.
yeah, she just defined it.
Because I think if you look in Costello's paper on topological conformal filtering, I think you would just take the full orientation preserving diffeomorphism group without taking pi naught, and then taking chains on that clusters. A priori, these could be different.
I mean, maybe it's just a jargon for up to isotopy or something. I mean, maybe it's nothing substantial, and it's just a fancy way of saying what the mapping class group is. So.
No, but I'm saying really kind of more the correct thing is the diffeomorphism group. And it just so happens for low dimensional reasons
That, okay.
that as a topological group up to weak equivalence, it's no different from its group of components. But that, I don't know that at this level of generality. I mean, I think this is a standard fact about closed surfaces that
So you want to say that connected component is contractible?
connected components are contractible. Yeah. So I think this comes up in Teichmüller theory.
Yeah. I don't know, but it seems that, for example, in connected component for torus, there exist loops which corresponds to rotation.
But I mean, any such mapping class group is generated by Dentwists, so probably, I mean, of course, it should be discrete.
But the claim is that any such thing will be isotopic to.
Yes, but
Like if you have a loop in of isotopes.
right,
like
but,
you can
but
contract
this is just rephrasing that connected component is connected.
Yes.
But you
No,
say that
but
it's
now if I have a
contractible.
loop of isotopes, the question is whether I can contract it to a trivial isotopy.
I think that's not true, but but in any case, we have connected some map for all diffeomorphisms which identical and bounded. So in principle, we can define it in the generality Chris mentioned.
Yes.
Continue.
Okay, so now I'll talk about some examples. So unfortunately, all the operations in these examples are the ones that we've already seen. And so I've been trying to kind of find examples of operations that arise from these constructions which are not the operations that we've already defined, like the BV operator or the Chassalan product, or their compositions, but the main difficulty is this, in this is that So if we want to define some operation which is strictly higher genus, then even, for example, if we take some surface.
Sorry.
Yeah.
So there is a term, there's some hypothesis. I don't know what it will be at this level of generality. But it says it's due to Earl and eels. So this is a famous theorem. So it depends on the genus. So if we consider compact oriented surfaces without boundary, you introduce boundary by adding mark points. So if it's genus 0 with 3 mark points, then the connected component of the identity is contracted. And the full group is a product of the connected component of the identity and a group of conformal automorphisms. In G equals 1, if you put in 1 mark point, it's the same kind of statement. And if G is greater than equal to 2, then the connected component is contractible.
Without mark points.
Without mark points. This is
interesting.
So in general, if we have many mark points, we don't know.
I think the more mark points you, yeah, that's a good question.
What's the question?
So if
When
we,
you put more mark points,
yeah, I mean, is there an example, or it's just a conjecture that everything is contractible?
in general, I don't know. But this is the theorem I was thinking about. So, I don't know, I'd have to poke around some more to see. This is a very short paper, like 3 pages long.
I mean, I believe that there aren't any difficulties that arise from this problem. But of course, it's an interesting one. Yeah. Okay. So what I was talking about is that if we want to define some strictly higher genus operations, then, for example, even if we have something like that, some comparisons like that, then the problem of defining the topological type of the classifying space becomes quite hard. So, for example, I couldn't find an explicit description for B mod S in case of such a surface. And so, probably because of this difficulty, later in the paper, the tool that is used to construct these spaces is constructing some category of graphs and then taking into geometric realization, which turns out to be quite, like, you can't just look at this space and understand what it is, really. So
this should be the same as the tours with the mark points,
yes? Yes, of course. But, I mean, even, for example, like, all the surfaces that we have here have non-zero boundary, but even if you just look, so for example, if we just look at a torus, and we'll look at the mapping class group of the torus, so it will be isomorphic to the modular group, and I don't know, maybe you know if there is an explicit description for this space, but
well, rationally, yeah. But you can work it out integrally as well. So it acts, I have to think of SL2, but for PSL2, it acts effectively on the other half line.
yeah, of course.
With
But
some stabilizers.
yeah, but the space of orbits will be.
Yeah, so you have these stabilizers. And so you end up with a kind of orbital fold model for the homotopy.
Yes.
And so you can actually compute the homology. There's a way to do it. I've seen it done. So
Yeah.
No, but even intervally, you can do it explicitly.
Okay, then maybe we can talk about it in a moment. Right now.
So the classical calculation would be of Serre in this book on trees.
Okay. So let's forget about this example for a moment. And consider just a cylinder. So we'll have that our incoming boundary is a circle, and the outgoing boundary is also a circle. And so first, let's look at the twisting that we want to define. So of course, it will be just trivial. So the twisting is trivial, and then the mappingless group of the cylinder is just generated by a done twist around the circle. So it will be just equal to z. So the classifying space will be homotopy equivalent to a circle, and then so then we have two operations, one which is parameterized by the zeroth homology of the circle, and the other is parameterized by the first homology. And so the operation which is parameterized by the zeroth homology will be just the identity from the homology of the loop space to itself, and the operation which is parameterized by the first class will shift the gradient by 1, and I believe that it will be the BV operator. So yeah, so it can be defined as just, we start with the homology of the loop space, then we kind of the identity to the first homology of the circle times homology of the loop space. Then it goes to homology of the product space, and finally goes to the homology of the loop space. So this map is trivial, then the other map is also trivial, and this map is given by the action of the circle on the free loop space. So yeah, so here is an example of two operations that we can get to this construction. So another example is if we take, instead of a cylinder, a pair of so if we take S equal to a pair of pens, so then the twisting will not be trivial. So the homology of the pants modular, the incoming boundary will be generated. So the zeroth homology will be equal to 0, the second will be equal to 0, and the first will be just generated by a cycle going from one incoming circle to the other. So as a virtual vector space, it will be equal to minus z, or yeah. Okay, so then if we take the mapping class group, then it will be just generated by the free den twists around the base of each pant, and these twists are independent, so it will be just z times z times z. Okay, so the classifying space will be S will be a 3 torus, and so if we fix the generator in a virtual space, then we will get the following identification. So it will be just given by the binomial formula. So I will, for brevity, I will not try to twist in. So the to z for I equals to 0 and 3, and to z cubed for I equals to 1 and 2. Okay, so and so if we take the zeroth homology of the zeroth homology of the classifying space, then the generator of this zero homology will define the Chest-Sullivan product from the tensor product to the homology of the loop space. Okay, so that's another kind of example. Why is this? I can't say right away, but we can try to look at it.
So it should be some sort of communication, but
So you say because it's
There's always such a thing in I think we haven't seen it yet because we were only considering operatic invariant operations with many inputs and one output. But in this case, you stated this way, there's the other direction as well. So I think we just haven't seen it yet. It's kind of like in a
unfortunately all the examples that are given, they all have one output. So
yeah, and again, so this product should have some degree.
yeah, so we have degree in here, and we know that this should preserve degree. So because we took the generator in the zero homology, then this map should preserve degree, I believe.
I saw that
Oh,
we introduced this product in an elementary way in one of the first seminars, and there was a degree.
there was a degree shift.
Indeed,
There
there should be.
should be.
It should be the homology of Lm shifted by.
Minus D.
Yeah, that minus.
Yeah, I think that mu already have degree shift, but because already in previous example, when you obtain BV operator, its degree should depend on D, right? And
But it's no, the degree of the BV operator is equal to 1.
That doesn't matter. It's an automorphism. So you can have, well, not quite, but I mean, anyway, you can shift the space back and forth. You'll always have this action of some operator of degree 1. But for the multiplication, in order for the multiplication to be between this thing and itself, with target is in itself, you need to shift. And let's see here how it works. Is there no
I mean, the only way that D participates in this formula is the tensor power of the twisting.
I can suggest a guess. Look, this homology, what you call the twist,
Yeah.
it is in degree 1,
Yes.
correct? So you take this and tensor it with itself.
D times, okay, yeah, so it should degree by.
If your construction remembers that degree, then it might be the answer.
Yes, yes,
So
that's probably the
maybe
case.
you don't want to consider virtual vector spaces, maybe you want to consider complexes.
Yeah, probably. I mean,
That is correct. You should think of it as a graded
Yes.
line bundle rather than a virtual line bundle. Where does chi live in this example?
where does
What is chi
chi?
in this example?
Okay, so it is.
Well,
It generates.
so it's modulo in, yes?
Yeah.
Um,
Oh, okay. So probably the reason that she writes that she says that it is a virtual vector space is that in all cases, because the incoming boundary is non-empty for each connected component of S, then the second homology will be equal to 0. Yes. And so then we will have just the 0th homology and the first homology, so that's why she just says that essentially this is the 0th homology minus the first homology. So
this seems crucial for
Yeah.
the formula you wrote for connecting sum.
yeah, so we shouldn't forget about the complex structure.
But when you take the determinant, you always get a line level on degree 0. No matter what you struggle with. Yeah, I'm not sure if this helps. Okay. So she doesn't say anything about a degree.
Mm. I mean, she says that we get a graded vector bundle that he.
No, but I meant about the degree on.
No, no. I mean, maybe she says something further, but
Let me look at what Costello says.
no. No, so when she goes on to actually define it, she just says that for an open closed cobordism, just consider the pair of vector spaces, which is the first and the zeroth homology.
But will you go into details of this theorem? So, why it's called degree D?
I will try to.
theorem?
Yeah, I
So
will try to.
Maybe the construction will delight us.
Right, so,
I don't believe that.
so what Costello calls the determinant. It involves the determinant, and then a shift by homological degree. And the shift is by, it looks like the Euler characteristic. Which is strange. And then when we take a power of that, there will be a shift. So here, what is the, so it is a graded line bundle of some degree. A degree depending on the Euler characteristic. And then when you take a deep power, so if it's 1 and you take a deep, yeah, so what do we want? I don't know which Euler characteristic is the problem. So the Euler characteristic here is what? It's H0 is 1, minus, so H1 is rank 2, so it's minus 1, yes?
The other characteristic of this pair,
No, I think of the surface.
of the
I'm not
surface.
sure.
Okay, so
I'm not sure.
Why
It would be minus 1. 1 minus 2 is minus 1. Is there no H2? There's no H2
No,
for this
no.
surface. This is a question if we consider the boundary or not. And then, if I take the deep power, I would get a minus 3. Now, does this work out? Let me think. It does work out. Exactly. So,
Yes, but you need the definition.
Yeah,
The
so-
reality would hold.
so
for
the claim
compensation.
is, so there should be probably a shift in what she calls det chi. It should probably be det of this space shifted by,
Mhm.
so that'll be a line level, and then it gets shifted in homological degree by the minus the Euler characteristic. This is what Costello says. Does she say nothing about this? Let me look at what she.
Uh,
I think I remember seeing something like this, but I can't find it.
What's it called?
High string topology. Yeah.
Yeah, but if there is any shift, then it should be invariant of the pair. Otherwise, you cannot achieve compatibility with connected sum formula.
Mhm. And this is why it's a little unclear to me what exactly Costello means when he says Euler characteristic of the surface. So he claims that in this sense, the determinant of this gluing will be the tensor product of determinants. So in particular, that would say that the Euler characteristic should sum.
But he explicitly says that we take the Euler characteristic of the entire surface.
Yeah, he says nothing about the boundary. Okay, let me see what.
I mean, I believe if we count in the boundary, then the Euler.
She calls it a graded vector bundle. She says this. She said we get a graded vector bundle, which we think of as lying in the degree minus the Euler characteristic of S relative to its boundary. So what does that mean? Euler characteristic relative to the boundary. Just Euler characteristic of
this. Because if we write the long exact sequence, so we have.
So in this case, is there an H3 statement?
So we have homology of this pair, then it goes to the.
Yeah, I think shifting by Euler characteristic of pair is
Yeah,
okay.
it's okay. Yeah.
Okay, hold on.
Because it's. Yeah.
Сейчас, а можешь прояснить в предыдущем примере, когда был просто цилиндр?
Да.
Я вот что-то перестал что ли понимать. Там относительно экологии просто тривиально.
Просто, да, прот 0, у нас там не было никакого случая.
Сейчас, и откуда надо появились какие-то там...
Значит, там было просто тривиальное расслоение.
Просто постоянный коэффициент.
Да.
But the number still works out in this case.
Yes?
Yeah, it's still
Okay,
a
yeah.
degree. So the point is that when we talked about the loop product, it was a map. Let me call H homology of the loop space. Then the loop product was a map from H shifted up d times, d times. Yes. And then if I shift all of this by 2D, I get a map. Well, let's say I shifted all of it by plus D. Then I could write it as H minus D H. And this minus D would be infinite, because this is a graded line bundle, has degree minus is shift by minus the Euler characteristic. So the minus D is exactly coming from this term.
Yes.
So it seems it's consistent in this one example. But it's
Okay. So
And this previous also.
in every example.
With the BB operator, you mean?
Yes.
Yes, their shift was 0. So.
Yeah. Yeah. So, okay, now we have two choices. I can talk about another example, or I can try to explain how these operations are constructed and kind of what tools are used while constructing them. So, okay, so basically, if we want to construct some classifying spaces like this, then the natural model for these spaces are the categories of ribbon graphs. So we can take just a moment. Mm-hmm. Okay, so we'll define the graph just as a set of vertices, a set of half edges, and two maps, S and I, and so the map S will be called the source map, and it will map the half edges to the vertices, and the map I will be a fixed point free involution on a set of half edges, and so you can understand this just as a usual graph, but the edges are kind of split into parts, or maybe split into parts just as oriented ones, and so the involution says which half edge corresponds to which half edge, and the source map glues these half edges to the vertices. So that is called a graph. And then, yes, okay. And so if we have a graph, then we can give it some additional structure. So consider the permutation sigma on the set of half edges, and what we want for this permutation is that its orbits will be exactly the half edges coming out of some vertex. So the permutation sigma just gives a cyclic ordering of half edges that come from some vertex.
Sorry, what you are asking for involution?
That it would be fixed point free. So each half edge will be glued to another half edge. Maybe, okay, I can, so what is it, kind of how to get from this combinatorial data the, like the real graph. So we can just take the set of vertices, then we can take the set of half edges, and then we can just kind of, the recipe is, so you take a half edge, then you look at the source map, you glue this half edge to the vertex, and then the involution says which half edge is paired with which half edge, and then you take this half edge and glue it like this, so you get an edge. Does this make sense? I mean, so what we did is we just took a graph, and then we just sawed each edge in half. And we remembered like which half corresponds to which half. So that's kind of a weird model for a graph, but it is convenient for our purposes. And so then we take this cyclic ordering, and given the cyclic ordering, we can then kind of construct the geometric realization of this graph. So it will be some two-dimensional surface with boundary called sigma gamma, and the recipe for constructing the surface is that you first take all the vertices of a graph and take some disks, two-dimensional disks that correspond to these vertices. Then for each half edge, then we take, for a fixed vertex, we take all half edges that come out of it, and we split this disk into intervals. Each interval corresponds to a half edge, and the order of these intervals corresponds to the ordering of these half edges by sigma. And finally, when we have such a splitting, we can kind of glue each strip. We can take a strip and glue it to one interval and to the other, and this is just dictated by the involution. So let me try to draw some kind of such a graph. So maybe there was an edge here. I don't know. We had an edge here.
You're telling us how to go from cyclic ordering of vertices to so-called urban graph? Or
Yeah, it is exactly a Riemann graph. Yeah. So the ordering dictates kind of the orientation of the surface. So okay. Yeah. So such graphs. So the graph G. Okay, I wrote gamma. The graph G with the permutation sigma is called the Riemann graph or a fat graph, and so yeah, so this will be denoted by gamma, and so these fat graphs, they form a category which is called fat. That's the harsh reality. A category of fat graphs, and so with appropriate morphisms, and I don't think that I will get into much detail about how this category works, but kind of the main theorem about it. It has been proved by different people, by Kontsevich, Iguza. Yeah.
I don't understand. You say that Riemann graphs are exactly the same thing
As a graph with an ordering on the vertices.
cyclic order.
Yeah, with a cyclic order. So like this graph, it sits inside the surface like a spine, and so I don't know. Maybe there is a good example that is shown
Yeah.
here. Yeah.
What I don't understand. I understand that the Riemann graphs allows you a twisting of the Riemann edges, right? And
But this twisting can be encoded in the, I believe, in the order, or okay. So you say that like if we I mean, maybe it is just not the case that any surface can be realized as a kind of as a Riemann graph, or
What's the coin?
so the question is like if we so probably we want to, like if we glue a strip, then we want to encode like the number of twists that the strip makes around the edge. I mean, I believe that this information is contained in sigma, but
yeah, well, if there are even number of twists, then this thing will become amorphic. But
yes.
I don't basically understand what happens
So
I don't think there should be any twists.
Yeah, but what the statement? The category of ribbon graphs is the same as graphs with cyclic ordering vertices. What was the statement?
no, I didn't make any statement. I said that we have like a combinatorial thing, which is a fat graph, and then we can get its geometric realization by doing this procedure, by taking the disks and then gluing the strips to them. I didn't yet make any statements. I mean, so the question is like, can every ribbon graph be realized as this?
More or less, yes.
Mm,
I think it depends what you mean by ribbon graph.
yeah.
That's, I think we don't need this.
Yes. Mm,
So the correct correspondence, one place is described, I think, is in this book of our Lando and Zonkin, called Graphs on Surfaces. So they give, I think, a definition of ribbon graph such that it is exactly a graph with a cyclic ordering of vertices.
okay, so
I mean, my difficulty is related to the fact that categories of such things are different, but maybe isomorphism classes are the same.
And we haven't even defined the category. I think the way in which this will be a category is something funny. Like what is it? But anyway.
I mean, I can tell what a morphism is, but so kind of naturally, the morphism in this category is a morphism of graphs, which just preserves this cyclic ordering.
So it sends vertices to vertices and edges to edges.
Or maybe, oh no, okay, I should have said.
You're allowed, it was like certain contractions.
Yeah, I think I also should have said something about. Okay, so if we'll. Okay, so define such a permutation. So if we take the composition of the involution and our ordering, then we will get some permutation omega, and the orbits of this permutation define the boundary cycles of the surface sigma gamma. So this is kind of trivial statement, but you just have to look precisely at the definition of the geometric realization. And so kind of a morphism of fat graphs is defined as a morphism of graphs which preserves these boundary cycles. So it should send the boundary component to a boundary component. So something like.
Boundary component means half edges that aren't attached to anything else.
I mean,
Or in the ribbon, the kind of edge of the ribbon.
yeah,
Yeah,
in the ribbon sense.
but by the way, in case when we regard them as ribbon graphs, then contraction does really nothing. So they all looks like strips attached to one disk.
I mean, if I take some boundary component that I contracted, then the graph changes.
I mean, contraction
Of
of
that?
strip is just
It kind of collects just everything in one point.
yes. And what's the statement? So
I will say, yeah, I will say it right now. So first of all, so we take surfaces S, and we take surfaces S with some marked points, and then we take their mapping class group. So the statement is that the geometric realization of this category will be the disjoint union of the classified spaces of mapping class groups and the disjoint union over all over all types of surfaces which should have positive characteristic.
And
So
at least one point, right?
I believe so, yeah. Yes, yes.
And positive value characteristic?
So I think modulo this point, it means. So like the surface should have a sufficient number of holes in it, of handles. I mean, if I correctly understand what the characteristic means in this case. I mean, does this make sense?
Say again what the morphisms are.
What the morphisms of this category? Okay, so okay, so we have some morphism of graphs, and then
Which means what? Vertices to vertices, edges to edges, and kind of respects incidence.
okay, yeah. I mean, we can say this like really precise. So if we have,
I'm not too worried about that. Just that's what we mean.
yeah, I believe so. So kind of just we can if we look at these maps, then we can extend them to the maps from the disjoint union to the disjoint union, and then we can extend the source map from the disjoint union to the set of vertices, and so this extension is just trivial on the vertices, and this extension is once again trivial on the vertices, and so a definition of a morphism of graphs in this terminology is just a map F of these sets which commutes with the extended I's and S's for these two graphs. Yeah, so I believe that it just means it coincides with the morphism of graphs in the usual sense. Okay, and so now the morphism of fat graphs is said to be a morphism of graphs which preserve each boundary component, and so yeah, so let's say what that means. Okay, so assume that we have a map, we have a morphism of graphs, and then we have a half edge H1 of the graph G1, and then what we want is that okay, just one moment. Hmm. Okay, so probably we just should. So let's look at some graph and so okay. I'm very sorry. Just. Okay, so let's draw an example. So consider such a graph, and then if we geometrically realize this, then we will have kind of the following surface. So this, and then it goes like this and like this. So we want to understand what boundary cycles are. So let's look in this case. We have this boundary goes to here, then it goes to here, then it goes to here, and to here. So here I have a boundary cycle. Now how can I deduct this from the combinatorial data on G? So as I have said, we have the following permutation. So I don't know, if we number the half edges of this graph, so like this, and then 5, 6, 7, 8. So then we'll have that sigma is just equal to the product of 4 cycles. And then we compose it with the involution on the half edges. So basically what I want to say is that the cycles of this permutation, we can view them like this. So for example, if we have an edge which goes from here to here, then kind of we have one half of it. So look at the half edges not as like actual halves, but as directed edges. And then we kind of have a half that goes like this, and have a half that goes like this. And so this half defines this part of the boundary, and this half defines this part of the boundary. And so then, if we take the cycles in this permutation, then it will give us exactly like this part of the boundary, then we glue to this part of the boundary, and so on. Okay? No?
I don't understand what's the point.
I want to understand how boundary cycles, how the components of the boundary of the geometric realization arise from the fat structure on this graph. So I say the recipe is such. So we take the composition of this permutation, then we look at this, then we. Okay. Yeah. So now we have to define what does it mean to preserve the boundary cycles, and so I believe this just means that we take a boundary cycle and then we possibly collapse some of its half edges, and then we map it just to another boundary cycle. So that should be the meaning. Okay. Okay. Okay, so
Yeah, but it seems that when you consider the geometric realization of some category on the left side, uh, you want to regard objects of this category as actually ribbon graphs and consider morphisms of corresponding topological spaces. It is correct. So, is this so then this isomorphism more or less clear since you have a category of ribbon graphs and you can choose for every graph as topological space one representative. Then every graph have some morphism to one such representatives, and it seems that these isomorphisms arise as just classifying space of
yes, yes.
groupoids corresponding to endomorphisms of
Yeah, so what
fixed ribbon graph.
yeah, so what you're saying basically is that take the connected component of the space,
Yes.
then
Yes.
take some fixed graph in it, then a morphism of this felt graphs will induce the morphism of topological spaces which will be homeomorphic.
Yes.
And then yes. So that's kind of the main idea, I believe.
Yeah, but
How is this compatible with what I just defined?
Yeah, it seems that geometric realization of fed graphs as topological spaces and discrete data like half edges and so on, this is not the same thing. Or at least is completely unclear.
You can write down, she does write down combinatorially in terms of data she gives what it means to be a morphism. And then it says that after passing through this ribbon graph, it means the following thing. I don't know if this is what you're getting at.
Yeah, but I again don't see twisting of.
There's no twisting by definition. The way you go from this to that involves no twisting. And
Why would
also,
you need a
in
twisting?
the reverse process also involves no twisting. You start with like a graph embedded in an oriented surface, and then you take basically a tubular neighborhood.
Yeah, for me it's not clear how you obtain, for example, damp twists which live on the right hand side in terms of any morphisms of graphs, ordinary graphs.
Well, what is pi1 on the left hand side going to look like? It's going to look like a sequence of morphisms which start and end at the same graph.
Yes.
So you want to know what generators look like?
Maybe, I don't know, like if we just take a graph with so just like, let's take a cylinder or an annulus. So probably if we want to twist it, then we can just take a cyclic graph like this and just like maps these vertices to this and this vertices to this. Just or
So I don't know what the generators correspond to, but I think that there is a explicit description, and I think it has something to do with a dual description in terms
Oh, okay, and I also believe that in the category fat, like, so originally, when this theorem was proven, the graphs in this category were considered, so each vertex must have valence at least 3. So you can have like a situation like this, or a hanging leaf. And so what Godin has proved is that if you add, basically if you add the vertices of valence 1 or 2, then this space will still be homotopy equivalent to the union of the classified spaces. Now, for the purposes of our construction, such a model does not suffice, but we can kind of improve it a little bit so it would work. And so now an open closed fat graph will be a fat graph gamma and such that its set of leaves is divided into 3 parts. So the incoming leaves, the outgoing leaves, and the closed leaves, and so we want to say that closed leaves will live inside, will be either the incoming leaves or the outgoing leaves, which will be called special. And so the special leaves which are not closed will be called the open leaves. And so basically what this means is that these leaves just correspond to the incoming and outgoing boundary components of an open closed cobordism. So if we look, for example, at this picture, then we can add a leaf here, maybe a leaf here, and I don't know, a leaf here, and so let this be the incoming leaves and this be the outgoing leaf, and also let's say that, for example, this leaf should be closed, and maybe add a ribbon around it. So then we will get a picture that looks something like this. So we'll have a component here, and we'll have a ribbon which goes around it. We'll have some component glued here. So here is a disk, and here is a disk which correspond to these 2 vertices. And we will also have some component which lives here. And so here's also the disk. And so because we said that, for example, this incoming leaf is closed, then this says that we take the boundary component which corresponds to this half edge, and then the entire boundary component should correspond to the incoming boundary of an open closed cobordism. And as this incoming leaf was open, we will say that just a neighborhood of the boundary corresponds to a cobordism. So kind of if we enhance the model of a fat graph like this, then we get a realization not just for oriented surfaces with boundary, but kind of for open-closed cobordism. And then the morphisms in this category are defined accordingly, and so the analog of this theorem also holds, so that the if we consider the category fat OC of open-closed fat graphs, then it geometrically realizes to the category of to the disjoint union of the classifying spaces for open-closed cobordisms. Yes. So that's kind of the instrument that that is used to construct these spaces. Okay, so now I will try to briefly say what will come next. So okay.
Sorry, what is the meaning of dashed circle?
I say that because this is a leaf, so because this is a leaf, I take the vertex, then I take the disk corresponding to this vertex. Because only one half edge comes out of it, then kind of this is the half edge. And so, like, the ribbon, when I glue the ribbon, then this boundary, it kind of comes around this circle, and I get something like this. So it's just, I mean, you can draw it just like you can draw this part smoothly. It doesn't really matter. It's just for illustrational purposes. So okay, so the next step in constructing these operations, which I will not prove whatsoever, is the following. So using this model of open-closed fat graphs, we can construct the following maps of spectra. So I believe we take the suspension. So once again, we take a surface, and we take the suspension spectra of the product VAS, and then look at a map to the thumb spectra of some virtual vector bundle K of S, where K of S is a bundle over a space which is just homotopy equivalent to this thing. So when I say M to the exponent of S, it says that it's just the space of maps from S to M. Okay, so although I will not define what is this bundle, but like the idea behind this construction is that if we want to first do this construction for above the elements of the category of fat graphs, and then extend it to the simplices of this of the nerve of this category. So kind of Godwin constructs some spaces called tab of gamma for a fat graph gamma, and these spaces then parameterize the maps of spectra from the suspension spectra of this space to the thumb spectra of K gamma. And kind of that, then this map extends to a map of the simplices, and in the end we get such maps. So yeah. And finally, just let's assume that we've constructed these maps of spectra, and now look at where the operations come from. So yeah, yeah. A break? Oh, maybe it is due. Yeah.
Or maybe it's too late for break.
Maybe I don't think that I have a lot more to say, so we can kind of, or we can do a break if you want. I don't know. Okay, let's just finish. So we have this tone collapse map from the suspension spectra of S modulo the modulo the incoming and the union of the incoming and outgoing boundary. So times S to the thumb space of this virtual bundle, and so then for this bundle we have a thumb isomorphism which sends the homology of this bundle with coefficients and some twisting of K of S to the homology of the homotypical limit of this over the category of some over the category of admissible fact graphs, whatever which means, which also should be decorated with some choices of in which morphisms are also enriched over some which is enriched over some kind of short exact sequences of vector spaces, and then we take the opposite of this category and we take the homotypical limit. And so here in the argument we have just maps from the fat graph to the manifold M. And so kind of dilemma is that the homotypical limit over this same category of M if we take here the outgoing boundary of the graph will be homotype equivalent to the disjoint union over all S of the spaces B mod S times M to the power of the outgoing boundary of S. So kind of we have this combinatorial model, then we take the homotypic limit, and it models such spaces for open closed cobordism S. And so now notice also that we have a natural map from M gamma to the maps from outgoing boundary. Here we just take a fat graph and restrict the map onto the outgoing boundary of it, and then we just have a map from this space to this space, which is induced by that map. Yes, and so, okay, just let me write it explicitly. So we have the homology of the homotypic limit over the same category of this, then it goes to homology of the homotypic limit over the same category of, and then this maps to just the direct sum over all classes of S of the homology of spaces S. So we kind of get this composition, and yeah.
I think we discussed this with you before. What was the last map? Just push forward along the projections.
Yes, over this. Yeah, but here I've taken the sum over all S's, so just right now it is in this form, but like of course to get the operations we'll have to project onto our desired component. Okay, so finally from the thumb collapse map that I have defined, we can get a map from the homology of S with listed coefficients times the homology of maps from the incoming boundary of S, and then this goes to the homology of the thumb space of the virtual bundle K, listed with coefficients in that K. And so finally, we have that, so we just compose this, yeah. So here we have this and this. It is the same thing.
Where does this determinant come in? So up at the top, you say there's a map from sigma infinity of this thing to the tone spectrum.
Mm-hmm.
I see. Maybe. how this is compatible with the twistings.
I believe that there just should be a typo there, maybe. I mean, just
It's fine. It always, as long as the twisting downstairs pulls back to the twisting upstairs, it should be fine.
it is true, yeah, but
And this is a general feature of twisted homology.
yeah.
If I have a local system, if I have a map, a local system on the target, then and I pull it back, then there'll be a map from twisted homology here to twisted homology there.
Yes. Yeah. So because this bundle pulls back to this bundle, everything works,
But
and
maybe because M is in there, so it must have been on D somehow. Okay.
yes, and so finally, just kind of what we want to do is just we have this map, then we have this map, and then we have this map. So we just compose them, and then this hits to just to the homology of M to the power of the outgoing boundary. And so finally, we can notice that this homology is exactly some number of tensor copies of the homology of the loop space and the homology of M itself. And then this homology is once again some number of tensor copies of the homology of the loop space of M and the homology of M itself, where the numbers are equal to the numbers of circles in here and intervals in here and circles in here and intervals in here. So kind of that's the main idea of how we get these operations. So sorry sorry that I didn't manage to be more precise about all this, but kind of the constructions that I used are too massive.
It's a
Okay.
shame that there seems to be not very much follow-up to this paper.
I mean, she talks about some conjectures just in the beginning, but I mean, kind of, for me, one of the problems here is that I don't really see how to explicitly write down these operations for fixed coordinates. So, like once again, so for example, if you take some simple case like just a genus 1 surface with
So with one incoming, one
Yeah,
outgoing.
yeah.
So the mapping class group of that is known, I think, maybe from this Bierman exact sequence, which allows you to forget a mark point. And then the kernel is pi1 of the surface at this mark point that we've forgotten.
I mean, I kind of maybe it just works like that. So we take this surface, and then what is the mapping class group? So, okay, sorry. What is the mapping class group of this thing? It is generated by the twist, yes? So it is generated by then twists around this part of the cylinder, around this part of the cylinder, and then also two then twists like this one and this one. So we have 4 generators, yes? And if we look at these generators, then these, and the pair of these are independent. And the relations on these 2 generators just give us SL2 of C. So it is just...
I think it's an extension of SL2 by a free group.
So you...
That's what the Biermann exact sequence would say. Oh no, it says that I think the mapping class group where you put a cap on one of them,
Yes.
it's an extension of that by the pi 1 of this surface, which is the free group on 2 elements.
Oh, okay. So you say that this is just... Or it is not a trivial extension.
Well, I don't know, it's just an extension. So, so I don't know how easy it is to compute the homology of this, but maybe the graphs will, I don't know. The other comment I wanted to make is that indeed, these spaces are homotopy discrete, these diffeomorphism groups. I found the reference, it's later than this Earl Eels. It's by some Japanese guy. It's called Homotopy Types of Diffeomorphism Groups of Non-Compact Two Manifolds. So at least in the non-compact case, it's not exactly what we want. But if it's non-compact without boundary, then except in some special cases, then the connected component of identity is contractible. So this is not quite our case, but it's another kind of result in that direction. So I don't know in our case what the answer is. I can dig around for the references. I don't know. I mean, it must be known, but I don't know how to do it. I'd have to think about this. If this is the correct answer, that it's an extension of this by a free group, and then how to compute the homology. So in the kernel, if it's a free group, there's only an H0, H1, that's not too bad. And for SL2, I think there's also only an H0 and an H1.
Mhm.
So the kind of spectral sequence associated to this extension is maybe pretty simple.
Mhm.
And so maybe you can really compute the answer of the homology. But I don't see how to do it like that.
Okay.
But it looks tractable in principle. Okay, thank you.
Yeah, thank you.
I'll send an email about the next talk. So we will no talk next week. Because maybe the faculty is closed, and also because there's some parenthesis sheet that I'm supposed to go to. But then the following